Hello guys, welcome back once again. It's been a little while since I posted a video, but today we're gonna do the chapter 7 of the MCAT Chemistry review, specifically the topic thermochemistry. So when we talk about the thermochemistry, thermo is a Greek word that means heat. It's just basically us talking about how energy transfer from systems to systems. And I could start off by going, through the laws of thermodynamics and, meandering my way through, which in effect is going to make the video longer. I hope we all basically know some fundamentals when it comes to thermochemistry. So I'm just going to start right off the bat and go into what is actually important on the MCAT, because the MCAT is never going to ask you what is the third law of thermodynamics. So to kick the ball rolling, first of all, we are going to start talking about systems. Now, see how I built my system of systems here. A little bit funny. Yeah. So when we talk about systems, sometimes or most of the time, students confuse the difference between systems and surroundings. Systems is basically the matter we are trying to study, the matter we are interested in. So system is the matter we are studying or observing. So the matter that we are observing is the systems over here. Now, if you take a coffee cup, say you have a cup of coffee like this in a styrofoam cup over here, right? And if we are just interested in studying how heat transfers between the coffee itself and the styrofoam cup, the coffee, just the liquid coffee, becomes the system that we are studying. And the styrofoam cup, the cup becomes part of the surroundings or the environment. So in this effect, we are going to be tackling the exchange of heat or energy between the coffee and then the cup with the surroundings. But if we want to consider the coffee, the liquid coffee and the cup together, then the coffee and then the cup becomes our system. And everything else around it, the air around it, your hand, whatever, becomes the environment. So technically, a system is not bound. It could shift depending on the more items that you are interested in to study. By so doing, if you take this coffee cup example over here, we can add things to the system to the point that the entire universe becomes part of the system. That is why entropy is defined in reference to the universe, because we can, expand the way. I could say the coffee cup and the human is my system. I could say the coffee cup and the human in the car is my system. I could say the coffee cup and the human in the car on the road is my system. So I'm adding more things to the system until I add the entire country of America, the entire continent, the earth, and the universe. And that will be one system. And everything surrounding it becomes our environment. So since that is taken care of and understood, there are 3 types of systems that we could encounter on our every day-to-day activities. And where's my systems that we can encounter, how the system is oriented. So for a system, we will encounter 3 types of systems. Let me do it this way. Isolated system. Isolated system. We have closed system and then open system. I could add systems to it, but I'm not gonna. So when we talk about isolated system, right, this system has been isolated, put to the corner by itself. So by definition, the isolated system cannot exchange energy and matter. So for the isolated system, we'll put into brackets here, no energy and matter. It doesn't exchange energy, neither does it exchange matter. The energy we're talking about here is in reference of heat energy, enthalpy. We will get there. So no energy and no matter. That is an isolated system for you. We've isolated it. It is by itself. Now, when we say closed system, like the coffee cup that I said, coffee cup is a closed system. Means when you have like a coffee cup with a top or the lid put on top of it, coffee cannot spill out of the cup, but energy, the heat in the coffee can transmit. That is why when you touch the coffee cup, you feel that it is hot, because the energy could pass through the styrofoam cup to your hand. Now that becomes a closed system. A closed system means you can exchange energy, but you cannot exchange matter. So energy, you can exchange energy. I just do the check mark that you can exchange energy, but you cannot exchange matter. That is a closed system. For an open system over here, if we say an open system, basically what we're talking about is that the coffee cup. So the coffee cup that we was talking about, if we take the lid off, now there are chances that the coffee could spill out. That means the matter itself, the liquid coffee, can spill out. That is an open system. The coffee can spill out, the energy can escape. So for that, you can exchange energy and you can exchange matter. That are systems for you. Now, these systems that we can encounter them in three separate examples, like isolated system, closed systems, or an open systems, can undergo changes. Now, when they undergo changes in thermochemistry, we say they undergo a process. And by definition, the process means they are changing some of their properties. Now, their properties include, I'll put it on top over here, the properties of this system are, let's say, the temperature, right? If it is gas, the pressure, right? If it is like some type of reaction, we can say the concentration, right? The concentration, right? If the system undergoes a process, and the process means changing one of these, the properties of the systems. So these, right, are, and then there are a few other more, but I'm not, you'll get the point. I'm not gonna list them all. These are the properties. So these are the properties of the systems, right? And as we said earlier, there are three types of systems: isolated, closed, and open. If any of these systems decides to change one of these properties, that changing is called a process. The system has undergone a process, right? So all of these changing to become these, if they change some of these, they become what we call a process. Now we got the process, how we got here into the process. So a process is basically a system changing some of its properties. It's a process, right? There are so many ways that a system can undergo a process, but there are some processes where some of these properties of the system are kept constant. And if they are kept constant, meaning they haven't been changed, it kind of alters the identity, which, in other words, the state of the system in a way. Now, there are, I think, four ways or four of these properties that can be kept constant. And keeping them constant, one we have over here, what we call, if we keep, all right, if we keep temperature over here constant and change any of these other properties, we say isothermal. So isothermal. Now, iso is a Latin word that means the same or constant. So isothermal, this is a hybrid of Latin and Greek. Constant heat or constant temperature means we are not changing the temperature. So let me put in over here and say constant temperature. Now, before I continue from here, a system always has its internal energy. Every system that you see, system always has energy. And the energy of a system is given by, which is the change in U, right, is equals to Q. Now, this Q over here is the heat added to the system, or in other words, energy added to the system minus the work done by the system. The W is the work done by the system. So over here that I said isothermal, constant temperature, meaning there is no more energy being done in the system because isothermal means I'm not adding any more heat. So according to this, according to my isothermal properties, the internal energy of the system, right, the internal energy, which is U, directly becomes my negative W, right? But internal energy can never be negative. So it is always the work done, the reverse of the work done. So then it becomes positive W over here. Now, once that is done, if we are supposed to plot, assuming that our system is a gas canister that have gas in it, if we are supposed to plot the pressure versus the volume graph like this, if I have my graph over here, which is my pressure on the y-axis and then my volume on the x-axis, and I am plotting the pressure against volume, I'm going to have a parabolic curve that decreases. So the parabolic curve is going to be something like this, right? Where I started from, say, over here, I started from volume A, and then over here, I ended at volume B, right? And I started at a zero pressure and then went up in pressure, or started from a higher pressure and then descend out a lower pressure. Now the area under the graph here, which is the area under this graph here, gives me the work done by the gas, which is W over here. So this internal energy is going to be the work done by the gas, which is also the area under the curve here. Now, if we want the ideal gas relation of it, we can say P is equals to nRT over V right here. So this is an isothermal condition whereby I am keeping the heat constant. Thereby, I'm not adding any heat to the system. Once that is done, the processes can also go. Now, if I keep pressure constant, right, I get what we call isobaric. Baric means pressure. So over here, if I keep pressure constant, I get isobaric, right? Now, keeping pressure constant would essentially gives me a similar P to V, a P to V graph. What's it? So the isobaric means that I keep my pressure is constant. Right now, since my pressure is constant, I'm going to have a similar, yeah. So isobaric, the pressure is constant. Once the pressure is constant, I could have my P to V. I cannot even draw a straight line. So I have this, my P to V over here. But now the temperature wasn't kept constant. It was the pressure that was kept constant, right? So if I'm supposed to draw the PV graph, now if I'm supposed to keep my pressure constant on this isobaric graph, which means the pressure is always constant. Let's say I started with 5 atmospheres of pressure. My pressure is always going to be 5 atmospheres. But then the volume might change. The volume can change because I'm not keeping the volume constant. So let's say I started with, let's say a volume over here, VA. I cannot technically start with a 0 volume. That means the gas exists in no space. It makes no sense. So if I start with a VA and then I ended VB over here as my final volume, now I get a square instead of a parabolic graph, right? So the whole process of isobaric gives you a square area. That, and the area of this graph is still the work done. The W is the work done over here. That is one process that a system can go through. Now, another process that a system can go through over here can be if I keep the volume now constant, which we called isochoric. So isochoric just means volume, or you can say isovolumetric, which means the volume over here is constant. Right. Now, if I'm keeping the volume constant over here, let's see how the PV graph is going to be. So I keep P over here and then V over here. I start with, let's say, 5 decimeter cube or 5 liters of volume. Starting, my volume is never going to change. So straight volume, but my pressure changes, right? So like it's if my pressure, I start with like 1 atmosphere, and then like I ended with another, say 3 atmosphere. It gives me a similar graph to this. Say I started the volume at 1, the pressure at 1 atmosphere, and then ended at 3 atmosphere, meaning I'm changing the pressure. The graph is still going to be similar to this one. Work done. But in this situation, one thing that you should get it right is that the work done, which is over here, right? If I keep the volume constant, technically the gas did no work, right? Let's say I have my canister still here, right? Which the volume is constant. And then I have some gas in there, all right? And I keep my volume constant. No matter how much I increase the pressure, the volume is not going to increase. The volume is still the same. It means the gas covered no distance, right? And we all know that the work done is equals to the force applied times the distance. So in some people say FD cos theta, where theta is the angle of the force. But yes, so it means the gas did not do any work. The gas didn't go anywhere. And then we say that the work done is FD cos theta. But D over here is 0. The distance is 0. If the distance is 0, it's rendering everything here to be 0, right? So with that being said, over here, there is no work done. And although the graph is going to appear as a square, there is still no work done. So over here, the work done is equals to 0. And the internal energy of the system is just equals to Q. There's a heat that we add into the system. That is one way a system can go through a process. Now, once the system has gone through a process, another way that a system can go through a process. Now we have isothermal, isobaric, isochoric. We now have the last and then the final way is adiabatic. Check the spellings for me. I think it's like this. Adiabatic. Now, adiabatic process, or when a system undergoes adiabatic process. Adiabatic is also a Greek word, means don't cross over. It just means do not cross over. It means heat over here is not crossing over. The system is keeping the heat, the internal heat that it have, constant. Now, once the system is keeping the internal heat that it has constant, let's see what the pressure. Yeah, so adiabatic, I think it's going to be like that. So the adiabatic process, you keeping just the energy constant, right? Meaning you are not adding any more energy into the system. Now, once you are not adding any more energy into the system, you're just keeping constant the energy. It means the temperature can change. So let's say you started with a temperature, right? Let's say you started with a temperature, and starting with that temperature is going to give you this type of graph, right? So the first temperature graph will be like this, right? Where let's say, not TP2 much. Let's say this one is called your TA, your temperature one, right? Shouldn't start from here. Let's say you started a temperature over here, and then it gave you this graph as TA, and then another temperature, right? That gave you this graph as TB, right? Now the actual process is going to be somewhere between these two, because you started with a temperature and ended with a temperature. So it's going to start somewhere from here and go very steep, and then pair up with the temperature that you ended up with. And the same thing, you are going to have a work done over here, which is going to be the work done under the graph. Same thing, but you are not adding any more heat into the system. So now this process, these are all the processes that a system can go through. I can pause. Yeah. Now, these processes themselves, which is isothermal, isobaric, isochoric, or isovolumetric, and adiabatic processes, they themselves can either be spontaneous or non-spontaneous. Now, so let's do it like this. These two, all these three, right, could come here and either be spontaneous, right, or non-spontaneous. Now, the spontaneous means that this reaction can occur by themselves without an addition of external energy. Like, you don't have to add anything from anywhere to the system and the reaction would occur, right? And if we are digging deep down into, thermodynamics, the spontaneity is when your Gibbs free energy is what? Negative. And your Gibbs free energy is given by, let me write this, your change in Gibbs free energy is given by your enthalpy minus your temperature change in entropy, right? So if our Gibbs free energy, and then this will either give us the reaction. Mind you, this is not going to give us the reaction whether it is endothermic or exothermic. It is going to give us the reaction whether it is endogonic or endogonic, right? So endogonic means that the system would release energy outside, right? And endogonic means the system will take energy within for it to perform its function. If the reaction is spontaneous, it means it's not taking any energy within to react. It will just occur by itself. But spontaneous reactions usually have a very high activation energy, so they don't really occur in like just like that in nature. For example, a match, you can never see a match just there burning itself. Although the tip of the match can spontaneously burn, by converting as atmospheric oxygen and mixing it together with, whatever fuel it is that they match, and it will burn to produce energy, releasing or heat outside, right? It doesn't occur by itself, meaning that if the match gains enough energy, right, to spark, the reaction occurs by itself. You don't have to keep on adding energy into it, but that energy is matched by you striking the match, right? Same thing in human processes or in human metabolic processes. Most of the reactions are spontaneous, but they are very much energy dependent. Due to this, we have catalysts, which will lower the activation energy of the human metabolic processes and making them occur at a much lower energy and for a shorter period of time. Because technically speaking, some of the metabolic reaction that happens in your body, if they are left to occur in nature by themselves without the introduction of any catalyst, it would take, some of them would take hundreds of years to complete. And by so doing, the human lifespan is not accommodated for this reaction to continue for that long. So that is spontaneous, right? And then your Gibbs free energy is negative. So the Gibbs free energy, the change in Gibbs free energy is negative, less than zero, spontaneous. Now, when we come here, which is non-spontaneous, it means you have to add energy into the system to make this reaction occur, right? So adding energy into the system would make your change in Gibbs free energy, the change in Gibbs free energy greater than zero, right? And now that would complete our introduction into thermochemistry. A little bit overview, just a little bit run through of it. As we said, is the matter that we are interested in. And we use coffee cup for an example. If we just want to study how heat is transferring between the coffee and then the cup itself, the coffee is our system and the cup is the surroundings. If you want to know how the energy is transmitting between the coffee and the cup with the system, the coffee and the cup become the system. And we can do this until we expand or get the whole universe in play. And a system comes in three types. You have isolated system, a closed system, and an open system. In an isolated system, no energy or matter can be transferred or interchanged. It is locked, it is stable, it is where it is at. No energy, no matter is getting in or getting out of the system. And for a closed system, you can have energy escape the system, but matter cannot escape the system. That is a closed system. And then for an open system, both energy and matter can escape the system or get into the system. It's vice versa. Now, a system, every system has properties that define the system as it is right now. And those properties include temperature, pressure, concentration, and some other properties. If the system changes any of these properties, it undergoes what we call the process. And this process it undergoes what we call process. And these processes are properties of the system. But there are so many ways that the system can undergo a process. But there are some processes where we keep some of these properties constant. And keeping them constant kind of, gives a phenomenon like a noteworthy or looking into a phenomenon of how the system is behaving. Now, isothermal is when we keep the temperature constant. When we keep the temperature constant, it means there is no temperature getting in or out of the system. Now, one thing that I did not add is that temperature depends on the average kinetic energy of the substance. So the temperature is just a measure of how hot or cold it is. The temperature itself is not heat. The temperature itself is not energy. The temperature is just a measure and depends on the average kinetic energy. And it is average because the system contains millions or billions of molecules. And these molecules are all moving at a different speed. So the instantaneous speed of these averages of these molecules are different for particles. The temperature gives the average scope or where it is. And you and I knows there are so many forms of measuring temperature. We have the Fahrenheit scale, the degree Celsius, and then the degree Kelvin. Now, under our classical chemistry, we know that a substance cannot exist under 0 degree Kelvin, which is absolute zero. But quantum chemistry says otherwise, but that is beyond the scope of MCAT. That is isothermal. We keep temperature constant. And we go to isobaric. Baric is pressure. We're keeping pressure constant. And when we do the plot or graph, we find this as our plot graph because we keep pressure constant. It's constant over here. Right. And then we have isochoric where we keep volume constant. And this was a little bit tricky because if we are, trying to do the graph, it is going to give us similar one to this, but all we should know is think outside the box and then know that if we never increase the volume of anything of the system never did any work. So the system not doing any work means we are not supposed to have a work done by that system. So that is isochoric. And then we got adiabatic, which is as keeping the actual energy, because adiabatic means heat energy cannot cross over from the system, cannot cross into the system or out of the system. And for that, the temperature although can change, the pressure can change, the volume can change, but the energy in the system is to be remain constant. So that the temperature change, this is our V1 graph, this is our V2 graph, and then the actual, work done by the system is going to be somewhere within these two temperature changes. And we also said that these processes can either be spontaneous, right, or non-spontaneous. When we say spontaneous, it is when our Gibbs free energy is less than 0 or is negative. Meaning that if we take the formula for Gibbs free energy, and then we want this to be negative, all we know is that the enthalpy change has to be very small for it to be negative. Meaning, if the enthalpy has to be very small, this enthalpy is also heat energy. If it's very small, it means we don't even have to add heat to the system. So that is why these spontaneous reactions, you don't actually have to add energy into the reaction. And when we think of energy, we think about temperature or adding heat into the system, right? And non-spontaneous, which is our Gibbs free energy, is greater than 0. If we want this to be greater than 0, this has to be big. The enthalpy has to be big so that whatever value this is, right, it will be minus and we get a positive value, right? So that is non-spontaneous process that the system can go through. We are going to continue from here into states and state function. And then from there, we will continue to finish the chapter. Thank you very much for watching this video. Please like and subscribe as I will bring the part 2 of the video. Peace out.